And moving on to the next point, to the ability to configure a production environment automatically, we're going to start with our first component, which is the master server. And to provision the master server, we've written a small Node.js script which does it for us. As you can see, it's called provision.js, and I'll be running it right now. So essentially what provision.js is doing is it's creating a droplet on DigitalOcean, which will act as a master server. The master server is the central server that is coordinating the activities of the rest of the application servers, which can auto-scale. The master server is responsible for listening to notifications from Jenkins, etc., and also handling the auto-scaling, essentially creating our app VMs. Looks like it's created. Now that the VM is created, we want to automatically configure the VM. To do this, we will run our Ansible playbook using the inventory file that this Node.js script has just created. So we've created a bunch of Ansible playbooks. This one is a playbook which essentially sets up our master, and similarly we have playbooks to set up application servers, playbooks to set up canary builds, etc. So the playbook is executing each of its components sequentially, and this will usually take a while. We're going to pause the video for a couple of moments until this is done. This usually takes 5 or 6 minutes, and once it's done, we'll be continuing from where we left off. It has been about 4 or 5 minutes, and as you can see, the Ansible playbook has run. It's installed all the dependencies, all the libraries that are needed, the Redis database, and has started the Redis server, and since set up the node, set up and installed node, installed Git, and essentially all the dependencies that we need, Ansible, forever, etc. And as you can see, it has made quite a few changes. And let's go back and see if the server is up and running. I'm just copying the IP address, and 2500 is the port for the master, and yeah, we can see that the master page is up and running. And let me just show you the Redis server as well. I'm just going to SSH into the machine. Well, actually, I'm just going to call start Redis CLI to demonstrate that the Redis server is running on the master. And let's just do a ping first, and yeah, it definitely seems to be working. So we have so far we have automatically configured the Redis server, the web server, which is essentially displaying this particular message right now, and we have also implemented an endpoint which is called the deploy endpoint, which essentially creates a new VM to be used as the application server. Right now we have no applications running, and let's just start our first application. As you can see, it has responded with the text message, and it should ideally have started spinning up a VM in the background. Let's check DigitalOcean to see if it has. As you can see, it is setting up the VM right now. Once the VM is set up, it would essentially run this playbook. It would essentially run this playbook to install Node, install Git, essentially install, get the Redis IP addresses, and then run the server, and essentially run the application server. This, as this like previously run, it takes a couple of minutes, and we should, in a few minutes, see the application server up and running. So let's just go back to Redis and see if the server has come up. So I'm just going to issue a lrange command on server's key starting from 0 and -1. Right now it's an empty list. I'll give it a couple of minutes and we should see the server pop up over here. I'm just going to pause the video and come back in a minute or two. As you can see, okay, the VM has been set up and looks like the playbook has done its job. And when we do an lrange now, previously it was saying it was an empty list. If we do an lrange now, we see our server coming up over here. So essentially, a server was spun up, and then it was also configured, all the software installed, and the application server was deployed on the server. And our database is maintaining a centralized state of all the application servers that are running. Currently, just one. And yeah, let me just show you the output from the Ansible playbook that we ran. So here we go. First, we just created a droplet, and then yeah, this is the output from the playbook, which essentially set up the server and pulled the latest changes from Git and then ran the server. Let me just show you the server in action. If the server is listening on port 3000, and if we open the port 3000, let me check the IP again. Oh, I think I got it wrong. If we open the server, it greets us with a hello world message, and it says that the server with IP 193.3.000 has served this request. And yeah, this demonstrates the fact that we were able to automatically spin up a server, configure a production environment, and then configure also, let me just show you. So the entire code base that gets pulled consists of the load balancer, the app server, and the code for the master node. And yeah, and therefore we were able to configure and essentially spin up our entire cluster, configure it, and run it, including database, application servers, and the master node, which is the centralized node that we have. Coming to the next part, which is essentially the ability to monitor the deployed applications. We've just now created another application server, and right now I think we have two application servers. Let's just check 0 and -1. Yeah, we have two application servers that are running, and if we check DigitalOcean, we can see that we have two application servers and a master server that is running. To essentially monitor our deployed applications, we're using this online cloud monitoring service, which is called as New Relic. New Relic provides monitoring services over the cloud. It provides plugins for Node.js, which we have included in our code, and also provides a system monitoring daemon, which we've installed on all our application servers, which sends back data to the cloud. Let me just run you through the UI for New Relic. So uh, both our application servers are live and the data is being reported over here. A lot of metrics are collected, such as CPU, disk IO, memory usage, etc. Let's just start with the first application server that we created a couple of minutes ago. And as you can see, we can get a detailed view about essentially the amount of memory it's been using so far, amount of IO, the load on the server, and the CPU utilization, which is really low right now because there are not many requests happening. And similarly, if you look at our second server, this was just created a couple of minutes ago. You will see that the time series data is much shorter in this case. But then we get a lot of useful information about memory, IO, etc., and also the processes that are running on the system and how much memory each of these processes are using. As you can see, most of it is being used by Node, which is to be expected. And the next important thing is the ability to set alerts when some of these resources have been overutilized. So right now we've set up a alert policy. As you can see here, this is a overview of our alert policy, and this is a more detailed version of it. For example, when in case of CPU, we say our policy says that if the CPU usage is more than 47% for more than 5 minutes, then it's time that we get notified about this event. The way we handle this event is essentially we set up channels, alert channels, and we have an email alert channel and a webhook alert channel. The email alert channel sends out emails saying that our servers are being overutilized, and our webhook essentially calls a slash post endpoint on our master server. We implemented a post endpoint at master server colon 2500 slash deploy. And whenever this particular whenever this particular webhook gets called, we essentially deploy new application servers so that the load gets balanced evenly and the utilization of these servers goes down. So, and yeah, right now we're gonna run a stress test on one of our applications and see if we get an email alert and see if our auto scaling functionality is working as expected. So let me just log on to one of these servers. This is one of our application servers, and here I'm just gonna run a td command to essentially waste a lot of CPU cycles. We'll just let this run for a while and see how essentially this should create a lot of load on our CPU. And if the threshold crosses 50%, we should ideally get an email, and also webhook should get triggered, which would essentially tell our server to spin up 2 more VMs to handle the extra load that's coming in. This will at least take 15 to 20 minutes, essentially 5 minutes for the trigger to get kicked off, and yeah, at least say 5 or 10 minutes. So we should be once we generate enough load, we will be back at the video and see if we can capture a live notification. We just got a notification from New Relic, which is saying that the CPU utilization has been more than 45 minutes, 47%, and I will just go ahead and stop this process. This demonstrates the email capabilities of our alert system. And let's see if this was able to successfully trigger the endpoint on our server, and if it was able to spin up 2 more VMs. Okay, right now it's spun up 1 VM to adjust for the load. And this VM should be configured using this VM will be configured using the Ansible playbook for the application. And soon we should see this particular IP inside our Redis server. As you can see, the load that we have run has caused the CPU utilization to cross the threshold of about 50% for more than 5 minutes, and we got an email notification for that. We've configured our server to our webhook to essentially spin up 1 VM whenever the load has increased. We could modify this number to a higher number if we decide that our application would need multiple servers whenever peak load is observed. Right now, we're just spinning up one. The setup of the third application server would take a couple of minutes. So we're just going to be back in a few minutes and let you know if everything worked fine. Looks like a third server has been created as well. And if we go to a DigitalOcean and copy the IP address, on port 3000, we should see our application running. Here we can see the hello world being displayed by our application. And in a couple of minutes, we should also see the new server, which was created and provisioned using the Ansible playbooks to show up over here. As you can see, a new server has been added over here. And as you can see, the server that has been experiencing loads and the server that was in a critical state is being flagged in the red color. So right now we have 3 applications running. Let me just quickly demonstrate. First IP on 3000th port is saying hello world, and the second IP on 3000 is also saying hello world, and so is the third IP. Essentially, we're running 3 different copies of our application server, and the next part of our project would be to demonstrate the load balancing capabilities, and essentially to show that we are able to use all 3 of the servers and distribute load across all 3 of them. And coming to the load balancing feature, as you can see right now we have 3 servers, and the information of all of these 3 servers is stored on the Redis centralized data store. This way our load balancer can get a list of all the servers and essentially pick one of these to serve the requests. The load balancing code is, let me just show you. Let me just log into one of the app servers, and inside the M3, essentially this app server was brought up using an Ansible playbook, and it essentially pulled the latest Git code and put it in the M3 folder. And as you can see, we have a whole bunch of applications that are pulled over here. The app server, which is the actual app server, the load balancer, which is essentially the code for the load balancer. The load balancer actually runs on the master node, while the application servers run on all the application nodes. For instance, load balancer would be running on this particular IP because this is the master node. And we set up the load balancer to run on port 8080, and its job is to forward the request to one of the application servers. As you can see, when I typed 8080 over here, it has redirected me to another page. If you look at this page, it says hello world, which is what our application servers were programmed to do. And as you can see, the application server is reporting that its local IP is 192.241.193, port 3000. So essentially, our load balancer has forwarded a request to this particular machine. As you can see, looks like our new relic has sent us another alert for increased CPU usage. Okay, coming back, if we run this and the load balancer is programmed to essentially randomly pick one of the servers from the list of servers that we have available. The list is maintained on Redis. As you can see, there are 3 servers, 48, 200, and 193. And if we refresh this page, we should ideally see the page being served by probably another application server. As you can see, now it's being served by the server 48, and if we refreshed again, now it's being serviced by 200. Essentially, it's randomly picking one of these 3 servers to service the requests. This is a load balancing implementation, and this has been implemented in JavaScript, and it's running on a main master server. The next feature that we've implemented is the ability to use feature flags in our code. And to use feature flags, we've taken the help of Redis, which is acting as the centralized data store in our application. So as you can see right now, when we open the application, we see the text hello world, which is served by multiple applications. And we've set a feature flag by the name of feature 1. And whenever the feature flag is enabled by setting the value of true, we should essentially see that feature being pushed to being triggered on all the applications. For instance, if I loaded my load balancer endpoint 8080, I should see that the feature, because of the feature flag, I see an extra piece of text over here. And this particular request was satisfied by the server at the IP48. And if we refresh again, we see even the server at 193 is enabled with this feature. Therefore, we were able to enable one feature across multiple applications by saving the state in a centralized data store. This is our implementation of the feature flag ability. To support Canary releases on our particular application, what we've done is in our setup, we've essentially created two different branches. One is the Canary branch, which is essentially the development branch, the more unstable branch, and the M3 branch, which is a more stable one. So all the application servers that we start are spun off the M3 branch, while the Canary releases, the more unstable to be tested releases, use the Canary branch. To demonstrate the Canary builds, I'm just going to make a small change in the README file over here and commit to the Canary branch. As you can see, it is being committed directly to the Canary branch. If I hit commit, this should essentially trigger a build on our Jenkins server. As you can see on the build queue, the Canary build has started. And once this build is found successful, this essentially issues a webhook and and tells our master server to spin up a Canary application. Let's see if that has happened. As you can see, the Canary a VM is being created for the Canary application. Once the VM is spun up, a Ansible playbook is executed on this particular VM to set up the VM and to install all the dependencies and to pull the Canary branch code base. This will take a couple of minutes, and as always, we'll give it a couple of minutes and come back once it's ready. Uh, After a couple of minutes, the setup is done, and the Canary server has been pushed to the Redis database. As you can see, when we did a null range, we can see a new server that has been added. And if we go back to DigitalOcean, we can see that the Canary server is the new server that was added. Canary server is just another application server, so we're just going to open it on port 3000, and it should say it should essentially, because the feature flag has been set from previously, this feature flag is it's displaying its properties, and also we can see that it is a build from the Canary server. So let's just set the feature flag, reset the feature flag. And let's just see if the load balancing is working with the Canary server as well. The whole idea is that we should be sending most of our requests to normal HTTP server, normal application servers, while a few of them end up going to the Canary server. Right now we have 3 application servers which are running the stable code and 1 Canary server which is running the not so tested code. As you can see, the first request that I made landed on the Canary server. Second one has landed on the normal application server. Third on the normal as well. Fourth on the Canary, and you get the pattern. So we essentially distribute load across more stable and Canary servers. This is our implementation of the Canary server.